In the previous lesson, we defined the cylindrical coordinate system with coordinates ρ, phi, and z, and derived the differential elements with the metric coefficient ρ. Now let's move to the third and final coordinate system, spherical coordinates. We'll define r, theta, and phi, show the transformation to Cartesian, and derive the differential elements dl, ds, and dv. The spherical coordinate system uses three variables, r, theta, and phi. R is the distance from the origin to the point, always non-negative. Theta is the polar angle measured from the positive z-axis downward, ranging from 0 to pi. Phi is the azimuthal angle measured from the positive x-axis in the xy plane, ranging from 0 to 2 pi. At every point, we define three unit vectors, E, R pointing radially outward from the origin, E theta pointing in the direction of increasing theta, and E phi pointing in the direction of increasing phi. These three unit vectors are mutually orthogonal and follow the right-hand rule. To convert between spherical and Cartesian, we use the geometry of the coordinate system. The x-coordinate equals r sine theta cosine phi. The y-coordinate equals r sine theta sine phi. The z-coordinate equals r cosine theta. Going the other way, r equals the square root of x squared plus y squared plus z squared. Theta equals the arc cosine of z over r. And phi equals the arctangent of y over x. The position vector in spherical coordinates is simply r equals RER. This is because ER already encodes both angular directions. Now let's derive the differential line element dl. In spherical coordinates, a small displacement has three components. In the r direction, a change dr gives dlr equals drer. In the theta direction, an angular change d theta corresponds to an arc length of r d theta. So dl theta equals r d theta e theta. The metric coefficient for theta is r. In the phi direction, the arc length is r sine theta d phi because the circle of constant theta has radius r sine theta. So dl phi equals r sine theta d phi e phi. The total line element is dl equals drer plus r d theta e theta plus r sine theta d phi e phi. The differential surface element ds combines two differential lengths. On a surface of constant r, which is a sphere, ds equals r squared sine theta d phi er. Both angular metric coefficients appear here, r for theta and r sine theta for phi, giving the r squared sine theta factor. On a surface of constant theta, which is a cone, ds equals r sine theta d r d phi e theta. On a surface of constant phi, which is a half plane, ds equals r dr d theta e phi. Notice that r squared sine theta appears whenever both angles are involved. The differential volume element combines all three differential lengths. dv equals dr times r d theta times r sine theta d phi, which simplifies to r squared sine theta dr d theta d phi. Compared to the Cartesian dv equals dx, dy, dz, the spherical volume element has an extra factor of r squared sine theta. This makes sense geometrically. Elements farther from the origin and closer to the equator sweep out larger volumes. Let's review. In spherical coordinates, the three variables are r, theta, and phi. The line element is dl equals dre, r plus r d theta e theta plus r sine theta, d phi e phi. The key difference from Cartesian is the two metric coefficients, r for the theta direction and r sine theta for the phi direction. The volume element is dv equals r squared sine theta dr d theta d phi. With Cartesian, cylindrical, and spherical coordinates all defined, we now have the three coordinate systems needed for electromagnetic theory.